Today we're going to start talking about changes of coordinates and specifically using change of coordinates to make double and triple integrals easier in certain circumstances. And today we'll concentrate on double integrals. So changes of coordinates, sometimes they let us express a problem more cleanly. There's lots of times in this class where we've had maybe some double integral and like, for example, integrating over a circle, when we set up the limits of integration, circles don't express themselves very naturally inside xy coordinates. We've got square roots in the bounds, it's unpleasant. And it would be nicer if we could use a natural coordinate system that cleans that up. So if we could do that, for example, in polar coordinates, where everything is expressed in terms of radius and angle, then it might be easier to do the problem that way. So polar coordinates, if you haven't seen them before, they're x is r cos theta and y is r sine theta. They measure every point inside two-dimensional space in terms of its distance r from the origin and the angle theta that it makes from the x-axis if you measure counterclockwise. There are some shapes that are expressed very, very cleanly using polar coordinates. And there are some functions that are expressed very cleanly using polar coordinates. But we can't just take a double integral and fire everything in by substituting x as r cos theta and y as r sine theta into it. We have to do it carefully because there's an area distortion problem that happens. If we think about our function that takes r and theta and produces r cos theta and r sine theta out of it, we can think of that as taking coordinates on the left-hand side in terms of r and theta and turning them into coordinates on the right-hand side in terms of x and y. And so it takes, for example, a little square shape that's near r equals 0 on this side and turns it into a very distorted kind of wedge here. Whereas a shape that has the exact same size and flavor in r theta coordinates but is farther to the right ends up being much bigger. And so if we're going to do substitution into polar coordinates, we have to account for the fact that areas are going to be distorted. Things that are closer to r equals 0 are going to be smaller, and things where r is large are going to be much bigger. And figuring out the right compensation factor is the subject of the change of coordinates formula. And more generally, we don't have to be tied to polar coordinates. There are lots and lots of different coordinate systems that allow us to say, hey, we've got a different way to think about this problem. So for example, here's a substitution. X is equal to u plus v and y is equal to u minus v. If we do that substitution, then it's going to take these lines, horizontal lines and vertical lines inside u and v coordinates, and it's going to turn them into diagonal lines inside x and y coordinates. That's going to give us a very, very kind of clean way to express diagonal things inside our coordinate system. That's a little bit better than we would normally deal with those just doing x and y coordinates. And so having that at our disposal is very handy too. So that's where we're going today.